Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Level 88, figure A shows the cross-sectional dimensions for the structural steel section known as C10 by 20 or channel with a nominal depth of 10 inches, weighing 20 pounds per foot. The American Institute of Steel Construction or AISC Structural Steel Handbook lists the following properties for the cross-section. Area is 5.88 square inches. I bar X is 78.9 inches to the fourth and I bar Y is 2.81 inches to the fourth. If two of these channels are welded together as shown in figure B, this is figure B, find I bar X and I bar Y for the resulting cross-section. So this is figure B, and this x-axis here still passes through the centroid of the individual channels. Therefore, I bar X is simply times 2 of this 78.9. So Ix or I bar X is times 2 of this 78.9. So 2 times 78.9. Therefore, I bar X of the resulting welded section in part B is, or section, resulting section in figure B is 158.8 inches to the fourth. Meanwhile, the IY or I bar Y of the two sections is not, this y-axis is not through the centroid of the channel. Therefore, we have to transfer the moment of inertia of the channel to this centroid here by transfer formula or by parallel axis theorem. So take note that the distance from the centroidal y-axis to the edge of the web is, outermost edge of the web is 0.606 as shown. So 0.606 inch as shown. So therefore, I bar Y is 2 times I bar Y of the channel, which is 2.81 plus area 5.88, then distance between the centroidal axis and the y-axis, which is the centroid of the two combined sections, is 0.606, then quantity square. So I bar Y or IY is 2 times 2.81 plus area, then 0.606 quantity square, where 2.81 is I bar Y or moment of inertia with respect to the centroidal y-axis of the single channel. Then the area is 5.88, and the distance of the centroidal y-axis to the centroidal y-axis of the combined section is 0.606, then quantity square, then the whole is multiplied by 2. So I bar Y is equal to 9.939 inches to the fourth. Level 89, for angles 3 by 3 by 1/4 inch are welded to a rolled W section as shown. Determine the moments of inertia and the radii of gyration of the combined section with respect to the centroidal x and y axis. So the x and y axis would be the axis of symmetry for this orientation of the wide flange and four angles. Then along with this problem would be the properties of this wide flange W8 by 31 and angles 3 by 3 by 1/4. So they are provided. So for the wide flange and the angle orientation, no problem with angle orientation because the legs are equal. Therefore, barred X, barred Y equal. I barred X, I barred Y would also be equal. So for the wide flange section, this is the table and it is W8 by 31. So let's put here the necessary data. Area 9.12, then the depth 8 inches, the moment of inertia with respect to the centroidal axis 110, that's needed also. Then the depth I barred y is also needed, 37.1, and the depth of 8 inches. Then for the angle, 3 by 3 by 1/4, which is this angle here, the area is 1.44. The I barred x is 1.23. Barred y is 0.836, which is also equal to barred x. That's why I barred y is also equal to 1.23 inches to the fourth. Then barred x is also 0.836. So let's transfer it here so that we can analyze this problem. So for the location of the centroid of one angle, so it's here. So the distance from here to the outer edge is 0.836 as shown. So that's 0.836. That is also 0.836. So therefore, if this is 5 inches, the distance of this centroid from the y-axis is 5 minus 0.836, because this is also 0.836. So 5 minus 0.836 is 4.164 inches. Then the distance of the outer edge of the flange from the centroidal x-axis is half of the depth. Since the depth is 8 inches, that's 4 inches. So 4 inches plus 0.836, the distance of the centroid of the angle from the x-axis is 4.836. So again, this is 4 inches, half of 8 plus 0.836, so 4.836 inches. Therefore, Ix is Ix of the wide flange, because this is also the centroid of the wide flange, which is equal to 110 plus 4 times quantity I barred x of one angle, which is 1.23, plus area 1.44, then distance 4.836 quantity square. So all of these angles will have distance of 4.836. So I barred x equals Ix of the wide flange, which is 110, plus 4 times quantity I barred x of each angle, 1.23, plus area 1.44, distance 4.836 quantity square. So I barred x therefore is equal to 249.6 square inches. Then we equate this to k barred x square area, where the area is 9.12 for the wide flange, plus 4 times 1.44 square inches for the angles. So 9.12 plus 4 times 1.44. So the area is 14.88 inch square. Then I barred x equals k barred x square times area. So 249.6 equals k barred x square times area, which is 14.88. So we can compute k barred x, which is equal to 4.096 inches. Then for moment of inertia with respect to the y-axis, this is also the centroidal y-axis of the wide flange, so it is 37.1. Then we transfer the moment of inertia of each of the angles, centroidal moment of inertia with respect to the y-axis of each of the angles to this y-axis here. So plus 4 times quantity 1.23 plus area 1.44, distance 4.164 square. So I barred y equals 37.1 plus 4 times quantity 1.23 plus area 1.44, distance 4.164 square. I barred y therefore is equal to 141.9 inches to the fourth. Then we equate that to k barred y square area. So 141.9 equals k barred y square area 14.88. So k barred y is equal to 3.088 inches. Level 90, two 20 mm steel plates are welded to a rolled S section as shown. Determine the moments of inertia and the radii of gyration of the combined section with respect to the centroidal X and Y axis. So here is the given figure. The rolled shape section has provided table as shown in this table. So this is S310 by 47.3 where the area is 6010 mm square. Then the depth is 305 mm and moment of inertia with respect to X is 90.3 times 10 to the 6 mm to the fourth, while moment of inertia with respect to the centroidal y-axis 3.88 times 10 to the 6 mm to the fourth. So for Ix, it is just Ix of the section, which is 90.3 times 10 to the 6. Then for this rectangular plates, we have to transfer it to the x-axis. So we need the distance of the centroid. So I bar x equals 90.3 times 10 to the 6 for the S shape. Then for the two rectangular plates, it is 2 times 160, 2 times 80 is 160 times 20 cube over 12 plus area 160 times 20 distance half of depth plus half of 20. So half of depth is half of 305 plus half of 20, which is 10. So 305 over 2 plus 10 is 162.5. So plus 2 times quantity 160 times 20 cube over 12 plus area 160 times 20 distance 162.5 square. So that's the moment of inertia with respect to this x-axis, and it is equal to 259.5 times 10 to the 6 mm to the fourth. Then for the radius of gyration, we simply equate this to kx square or k barred x square times area, and the area is equal to 6010 plus 2 times 160 times 20. So 6010 plus 2 times 160 times 20, 160 mm wide by 20 mm thick. So area is 12410 mm square. So 259.5 times 10 to the 6 equals k barred x quantity squared times area 12,410. So from there, we can compute k barred x or radius of gyration with respect to the centroidal x-axis of 144.6 mm. Then for IY, this is the centroidal axis of the S shape, so it is 3.88 times 10 to the 6, while this is also the centroid of the rectangular plate, and it is 2 times because there are two rectangular plates, 2 times 160 cube times 20 over 12. So I bar y equals 3.88 times 10 to the 6 plus 2 times quantity 160 cube times 20 over 12. So I bar y is equal to 17.53 times 10 to the 6 mm to the fourth. Then we equate that to k barred x square times area 12,410. K barred y squared times area 12,410. So k barred y is equal to 37.58 mm. Level 91, a W8 by 67 section is joined to a channel 10 by 20 section to form a structural member that has the cross section shown. Calculate I bar x and I bar y for this cross section. So here's the given figure and data for the channel. So I bar x 78.9 inches to the fourth, I bar y 2.81 inches to the fourth, and area 5.88 inches square from the previous problems. For the W flange 8 by 67, area 19.7, I bar x 272 square inches, inches to the fourth, and I bar y 88.6 inches to the fourth. Now, since we have two sections, although the centroid of the combined section still lies on the y-axis, then we need to locate that. So for our solution, this is the orientation of the channel. That's 0.606. This is 10 inches. And thickness of the web 0.379 inch. That one. So therefore, the y-axis is the x-axis of the channel. This one, you look at the orientation, it is flipped here. So the y-axis is the x-axis of the channel, while the centroidal x-axis is the centroidal y-axis of the channel. So that's only for the channel. For the wide flange, it's the same. The x-axis, centroidal x-axis is also the x-axis, and the centroidal y-axis is also the centroidal y-axis for its orientation, which is this. So let us say this is the centroid of the channel. The distance of the centroid of the channel from the outer edge of the web is 0.606 as shown, 0.606 inch. Then this is the centroid of the two sections, then centroid of the wide flange alone. So the distance of the centroid of wide flange to the top edge of the wide flange from here is equal to half of the depth, 9/2, then plus thickness of the web of the channel, which is 0.379, then that distance would be 9/2 plus 0.379. So that distance is equal to 4.879 inches because our reference in computing YG is this upper edge of the channel. So if this is YG, we can compute YG by Varignon's theorem. So the area is equal to area of the wide flange 19.7 plus area of the channel 5.88. So the area therefore is 25.58 square inches. Then by Varignon's theorem, 25.58 times YG is equal to 19.7 times 4.879 plus 5.88 times 0.606. So YG is equal to 3.8968 inch. Then we can now compute IGX or I bar X here. So we transfer both moment of inertia option of each section. So this distance is equal to 4.879 minus YG. So IGX or I bar X equals I bar X of the wide flange, which is equal to 272, then plus area, its area 19.7, then distance between this centroid and that centroid is 4.879 minus YG, 3.8968, then quantity square. While for the channel, this is, take note, that is IY of the channel, and IY of the channel is 2.81 plus its area 5.88, then distance square is 4.879 minus 4. The distance between the centroid and this G here is YG minus 0.606 inch. So plus 2.81 plus 5.88, quantity YG 3.8968 minus 0.606, quantity square. So this distance is squared. So take note, this is IY of the channel because the orientation is different. So this is this y-axis here, which is this horizontal axis here, parallel to the x-axis. So that's the reason. So I bar x equals IGX equals 357.5 inches to the fourth. Likewise, for I bar y, it's not difficult because this is the centroidal y-axis of the wide flange. This is also the centroidal x-axis of the channel. So therefore, I bar y or IGY is simply 88.6 plus 78.9. So I bar y equals IGY equals 88.6 for the wide flange, I bar y. Then this is I bar x for the channel. Take note, this is the x-axis for the channel. So that's why we have to add 78.9. So I bar y or IGY is equal to 167.5 inches to the fourth.